Hey everybody. Today I want to show you about a new tool called Parametric Equations. So, a parametric equation or a parametric function can describe lines or curves using a new variable, a new parameter, if you will. And that parameter is usually the variable t because it typically stands for time. So, if we make a graph using parametric equations, you can do that on the calculator by switching modes and going into parametric mode. So press mode and find the PAR option. Your calculator's probably in function. That's the most normal equation. But anyway, if you do that, then when you press the y equals screen, instead of seeing a single y equals, you'll see equations that come in pairs, because you need an equation for x equals and y equals. And the variable button, if you press that, instead of getting an x, you'll get a t, because that's, again, the parameter that's usually used. If you press the window button, you'll get new window settings. So instead of just your typical x min max scale and y min, y max, and y scale, you'll also get a t minimum, t maximum, and t step. And so those will be some new things that we'll have to figure out. What do they mean? Why do we use them? What should we set them to be? And so forth. So let's look at an example. We're going to consider the location of an object. Actually, this comes from a physics class, so this could be a ball or something that is thrown in Earth's atmosphere, and so it flies up and so forth. But anyway, you don't need to know that. We're going to make the equations here, and we want to know if x is defined as 15 times time, and y is defined as negative 16 time squared plus 45 time plus 3. How do we make that graph? So, assuming you've already made your switch into parametric mode, let's see what we need to type into our calculator to make this sort of thing happen. First, go ahead and press the y equals screen, and you can type in to the equation 15t. Again, to get that t, press the x, t, theta, n button that you normally press for an x. And then for the y equals, we'll type the negative 16t squared plus 45t plus 3. Be careful that you use the negative sign instead of the minus sign. My computer can't make it look like a negative sign, but that might cause an error later. And I want to produce a graph on a particular window that looks like this. And so to make that happen, let's type in x scale settings and y scale settings. So you press the window button and you can type in numbers. For the x-axis, we'll go from 0 to 40 by 5s. And for the y-axis, we'll go from 0 to 60 by 10s. Oops. But the new settings are going to be these time settings up at the top. And so for now, I would suggest that you type in for a t minimum 0, for a t maximum 10, and for a t step maybe 0.1. And if you were to hit a graph now, you should see a curve showing up. I'll do my best to kind of sketch it. I'm not a very good artist, so do I have a sketching tool? Maybe not. But anyway, it should start here and go up and kind of come down here-ish. And then your calculator will be thinking for a little bit, and then eventually the graph is done. So that's the path that ball took through the air. And then we can answer all sorts of different questions about it. For instance, what's the starting position of the object? To answer that question, if you know where to look in the formula, you can just answer it right away. But if you don't, if you press the trace button on your calculator, you'll have settings for time and an x and a y position usually. And so if you go to time equals 0, which is probably what it starts off with, it should have as its initial position a 3 and a 0 for x and a 3 for y. trying to do this from memory, so I hope that's right. Again, if you hit trace and then you press left and right, now you should see your cursors moving, and it's moving in specific time intervals. It's moving 0.1 seconds at a time, and that's because you told it to when you chose the t-step of 0.1. So if you move yourself over until time is 2 seconds, then you can answer this question about where the object is after 2 seconds. That would be, shoot, I don't have that one. And it's going to take me a long time to get it. So it's somewhere around in here. I want to say it's like 3028-ish or something like that. So I'm going to at least fill in the 30, and then you guys can figure out what the y value was. So now there is a small change I want to make. And for example number 3, we're going to look at what happens if you want to graph the position of the ball for every 0.2 seconds for 2 seconds. And so that's a couple changes in our window settings. Our equation's still going to be the same. I'll still use the same x, min, max scale, and so forth. But this time, instead of graphing for 10 seconds, which is why the calculator took a little while to finish the graph if you paid a close attention, I just want to graph it for 2 seconds. And instead of having a theta step of 0.1, let's have a theta step of 0.2. So you can hit graph, and you'll see that the curve draws and then it stops a certain way. But I want to encourage you to go back to the y equals screen and go up to this little line here and temporarily turn it into a dotted line instead of a solid line. So you can do that by hitting enter on it a couple times. It'll cycle through the different things. If you do that, and then if you hit graph, you should see this sort of picture instead. And this is how your calculator thought. It started by putting a 0 in for t, and then it put a 0.2 in for t, and a 0.4 in for t, and it plotted all these different points. And those are the locations of the ball at each of those different times. And so this last one was the answer to that last question that I didn't remember the coordinates for, right? 2 seconds. I think it was 30, I want to say 28. Maybe I have it memorized right. But anyway, those are a couple of changes that sometimes happen. And so depending on what your time settings are, your graph might be taking forever to graph, or it might not be accurate enough. And so you can change those things if you need to. Let's look at a different application. So parametric equations give us another tool that we can use to create a line. And so to create an equation in parametric form, you need 2 things. You need some sort of a direction vector. That's an orientation, or that's the slope, if you will. In fact, you could put a rise in for delta y and a run in for delta x if you're on a regular 2-dimensional plane. And then you need some sort of starting point. And so that's location. It's similar to the b in y equals mx plus b, but it doesn't have to be the y-intercept. It could be anything. So that sort of template works for both 2-dimensional lines, but this also works in multi-dimensional space. So if you have a line that's going through 3D space, you simply have a z equation mixed into that as well. So let's look at a 2-dimensional example a moment. So what if we wanted to write an equation for the line that goes through the points 2, 5 and negative 1, 9? So to do that, we need an equation for x, and we need an equation for y, and then we've got our time as the variable in this problem. And so the number in front of x and in front of y is going to be the slope between these 2 points, the rise and the run. So if I look at from 2 to negative 1, that's a decrease in 3 steps. So I'm going to write for my x variable, or the number in front of x, a negative 3. To go from 5 up to 9, that's a rise of 4. And so I'll put a 4 here. And then I need to pick one of these points to be my starting point. I was kind of thinking of starting at 2, 5 and going to negative 1, 9. And so let me put the 2 in for the x start and the 5 in for the y start. And this equation then, if you were to type that into the calculator, would form a line. You would see that it starts at 2, 5 and goes off in one direction. If you want it to look like it goes in both directions, choose your time settings to not start with 0, but to start with some sort of a negative amount instead. Let's look at another application. So here we've got two planes that are traveling. This is an actual airplane as opposed to the three-dimensional flat surface plane. And so if an airplane starts at 20-240 and is traveling south at 100 miles per hour, and another starts at -10-100 and is traveling east at 50 miles per hour, the question is, are they going to crash, right? Are they heading in the same direction? Where are they at any given point in time? There's lots of reasons why we might want to look at this. So let's start off with some sort of a scale that might make that happen. So the first plane starts at 20-240, and so that would be somewhere around in here, and it's traveling south at 100 miles per hour. And then the other plane is starting at -10-100, which would be here, and it's traveling east at 50 miles per hour, which would be going this way. So it certainly looks like they might be in the same place at the same time. Let's see if we can create equations that model both planes. So first, if we take this first plane that starts at 20-240, we can put that location in, 20-240. I can make that a little bit bigger. Oops. There we go. And we know that it is traveling south at 100 miles per hour. And so that means it has no horizontal component. And so I can put a 0 in there. And it's going south at 100. According to normal x, y's, and so forth, south is down with the y coordinate, so it's a negative number. So I'll put a -100 in here. In this case, time represents times in hours. And so if you wanted it to go a little bit slower, you might have your time settings be a little bit smaller than 1s. I'll show you that in a moment. Let's get the other equation in here. So the other plane, it starts at -10-100. So I can put in that x and y coordinate. And then its slope, if you will, because it's traveling east, it has an x component. It is traveling at 50 miles per hour. And then its y component is that it is not moving north or south. It's going purely east. And so that will be a 0. So if we wanted to make a graph of this then, you could go to your x and y equals screens, type these equations in. If you do that, I would suggest switching your mode over to this mode where you've got a little cursor that will look like a plane that's producing a little contrail, which is kind of fun. And then for some window settings, by the way, I'm not sure if you can hear my daughter screaming, but my wife's got it under control, so it's pretty loud and embarrassing here, but yeah, I think she's just being a stubborn 3-year-old. Love her to death. So let's see, window settings, according to what I had, was about -100 to 500 by 100s. And from -300 to 300 by 100s. And then for time settings here, I think I'd start at 0. And then I'll graph a couple hours, maybe 2 hours, 3 hours maybe into the future. And then for time step, instead of just going by 1s, because that'll graph like instantly, I think I might suggest going by minutes. That would be 1/60. If that's too slow, you could go by 5-minute jumps, 5/60s or something like that. So I'm going to let you guys try to make that graph, but spoiler, the planes don't crash. They're never in the exact location at the same time, but if you just looked at their paths in the sky, it might look like they did. One last application. This one is how to make a circle or an ellipse through parametric equations. So to do that, your equation is something times the cosine of something. This is an equation set up in degrees. That's why the 360 is there. That's a full circle. And then a center point over here. And a similar sort of equation for y, but using sine instead because sines are heights. And so the question is, can we use this to model, say, the solar system? And so if we wanted to do that, the equations that we're going to need will be shaped like this. I'm going to set one up for Earth and then another one up for Mars. And we're going to use that to graph their orbits and see when they ever line up again. That's what a conjunction is. So for the equation for Earth, or the equations for Earth, I'm going to set up the radius of 1 times the cosine of 360 over Earth's period. That is, how long does it take for Earth to orbit the sun? And that's 365 days, multiplied by time. And then I need a x-coordinate of the center. That would be, where's the sun located? And I'm just going to call that 0, 0. So there's an equation for the horizontal position of the Earth at any given point, any given day of the year. If we do a similar sort of equation for the y, we would have this. And we could hit graph and see this, but there's definitely some window settings we need to fix. Why don't we think about that a little bit? So for window settings, this is a really small scale. We're drawing things in terms of Earth radiuses. That's what an AU is. And so I recommend for this particular window going from maybe -3 to 3 by 1s. And then vertically, maybe -2 to 2 by 1s. I like to have a little wider x-axis than a tall y-axis, just because the screen's rectangular. And this will make it look a little bit more accurate when we graph things. And then the time settings. This is going to be, in this case, time is measured in days. And so in order to see a full circle, I'm going to need to do at least a year, 365. And so I'm going to start at 0 and go a couple years into the future, maybe 1,000 days. And then for time step, if you do it by 1, it's going to take forever to graph because it's got to plot 1,000 Earths. And so you might want to go up by 5s or 10s to speed things along a little bit. Anyway, now you should be able to hit graph and see the Earth rotating around. It should be kind of cool. But before we do that, why don't we add Mars's equations in here too? So if we put their orbit in, they're a little further out at about 1.5 AUs. And so the inside of the cosine is going to be 360 degrees divided by 687 days for one Mars orbit times time. And again, the center point would be Mars also goes around the sun, and so we can put a 0, 0 for x and y. And we'll finish that up. 1.5 sine of 360 over 687t plus 0. That would be its y value. And so I made a video of this earlier, so I'll show that to you second. We'll watch as we make these graphs. If you need a particular setting, go ahead and hit pause at a particular point. One thing I'd call attention to in this mode screen, make sure you're in parametric. But I also switched over to simultaneous mode, which graphs the two windows at the same time. And by two windows, I mean the two planets at the same time. So anyway, here's the equations. Nothing new here. Here's the window settings I suggested you type in. And now we'll hit graph, and we'll see there's Earth circling its way around. Mars is a little slower. And the question was, when is the next conjunction? So a conjunction is a astronomical term for when the sun and the moon or the sun and some planets all line up. And so we're getting close to that point. right about now, those are all lined up. And so if you wanted to find that, if you hit trace and kind of walk your way around, eventually right around here was when everything lined up again. And somewhere around 770 days. And so what that means is if you were to track Mars in the sky over the course of 770-ish days, that's how long it takes to eventually line back right up with the sun again. So anyhow, thought that might be an interesting application for you. Hope you can do this. Hit me up with any questions that you might have, and I'll see you next time.